So this video is going to be on reinforcement learning, specifically how reinforcement learning problems are set up, as well as Bayesian reinforcement learning, which is a specific method for solving reinforcement learning problems. This will be useful to have in mind when we later discuss Vanessa's research agenda, as well as when we talk about Infra-Bayesianism. Reinforcement learning is a mathematical framework for expressing how an agent should navigate some environment in pursuit of some goal. The theory has been contributed to by several people, including B.F. Skinner, who appears on the right, and who trained pigeons to play ping pong using reinforcement learning, Sutton and Barto, who appear in the middle and did lots of the seminal work on temporal difference methods, as well as wrote the seminal textbook on reinforcement learning, and Richard Bellman, who appears on the left, who invented dynamic programming, which was a method to solve Markov decision processes. So what is reinforcement learning? Well, reinforcement learning is set up as a sequence of decisions. You have an agent acting in an environment that takes an action, gets an observation and a reward, and uses this with previous information to take a new action, and this process continues. At each step, the agent receives some observation O, takes an action A, and receives some reward R along with a new observation, and this repeats till we get to a terminal state or carries on forever. The agent and environment interact only through these input-output channels, but the environment will evolve independently from the agent as well. You can think of reward as a treat for the agent. The goal of the agent is to maximize its cumulative reward, and reinforcement learning techniques are methods to learn behaviors that lead to this goal. This could be applied to a lot of different settings. You might ask, how general is this framework? There is a hypothesis called the reward hypothesis, which states that all goals can be described as the maximization of expected cumulative reward specified by some reward function. This probably isn't true in full, but it's incredibly difficult to find goals that you can't express as maximizing a cumulative reward. It's particularly important to note that reinforcement learning can capture cases with delayed rewards, since the agent is trying to maximize its cumulative reward, so it may make decisions that cause it to miss out on reward early, but lead to more reward later. So games that involve planning early steps with the intention of getting delayed rewards are also captured by this framework. To speak about how general this framework is, we can look at examples of reinforcement learning problems. Very simple cases like grid worlds, where you have some agent moving around trying to get to a goal square. These can be expressed using reinforcement learning. We also have video games like Atari games such as Breakout, or more complicated video games like racing games. Also, self-driving cars in the real world can be captured using reinforcement learning. We also have cases of gambling, like how to choose which slot machine to play on and how long to play on them, as well as things like poker. These can be expressed using reinforcement learning. We also have more complicated things like trying to perform stunts with a toy helicopter, such as front rolls or 360 spins. Before we talk about how many reinforcement learning problems are set up, it's important to talk about some simplifying assumptions that are often made in reinforcement learning to make life easier. In general reinforcement learning, the agent would use everything it's seen to decide what action to take. Specifically, every observation it's seen, every reward it's received, and every action it's taken. This set of things is called the history of the agent, and all of this could be useful in deciding what the next thing to do should be. This becomes quickly intractable though. You can imagine trying to do this for yourself, trying to make a decision based on everything you've seen and every action you've taken. It just becomes impossible. It's too complicated. To make life easier, we make a couple of assumptions about the environment and the observations to make this problem tractable. The first assumption we make is that the environment has what's called the Markov property, which is pithily said as the future given the present is independent of the past, and it's expressed using this equation here. Basically, the idea is that everything that's happened in the past will not be helpful in me trying to decide what the optimal decision to make is in the present. All I need is the present state to decide how I should act and how it will influence what happens in the future. The grid world here is an example of an environment that satisfies this property. If I know I'm in the space where the A is, that's all the information I need in order to get to the top right corner. If I was told I was in the bottom right corner 10 time steps ago, that information isn't helpful in deciding how I should behave to get to the top right corner. In the last video, Jack talked about independence when talking about Bayesianism. The Markov property, in some sense, is the simplest relaxing you can have of independence. Independence says I can throw away all the information from the past since it's not going to help me, and I can focus on the current distribution. In Markov, you say I can throw away almost all the information. I can throw away all of the information except the most recent observation and just keep this information and use that to make decisions about what's going to happen in the future. The Markov property is important, but it's not enough to guarantee that I won't need the full history. We also need the environment is fully observable, which means there's no part of the environment that we don't get to see. We get to see the full state of the environment. As an example, you can think about the game of chess. This is fully observable. There's no part of the board that I don't get to see. As an example of a game without this property, we can think about poker, where I can't see my opponent's hands, and that information could be useful when deciding how I should behave. So there are cases that aren't captured by this fully observable condition. As another example, we had this grid world here, which was fully observable. But if we pretend the grid world is on a foggy day, so I can only see one square around me, then now, even though the environment obeys the Markov property, if all I can see is this smaller square, I will need to know where I was in the past to make decisions. So Markov isn't enough. I do need fully observable. If I have both of these conditions, the environment is called a Markov decision process, or an MDP. When I only have the Markov property, the environment is called a partially observable MDP, or POMDP. So now that we're talking about Markov decision processes, we can formalize this idea. A Markov decision process is a set of objects called a tuple, specifically the objects S, A, P, R, and gamma. S is the state space, which characterizes all the possible ways the environment could be. So for example, in our grid world, the agent could be in any of the 9 grid squares, and these 9 states perfectly capture the state of the environment. A is the action space. It's the set of actions that the agent can take. So in the grid world example, there are 4 actions, left, right, up, and down. Both of these spaces can be continuous or discrete. Reinforcement learning can handle either of these cases. P is the state transition function. It captures how the environment will evolve based on actions I've taken, as well as how it will evolve independently from the agent. The probability that I end up in state S primed, given that I took an action A from state S, is given by this number. This can be deterministic. For example, if I'm in the bottom left state of my grid world and I take the up action, I'll definitely end up in the state above. But in more complicated environments, this quantity is going to be a probability distribution over S primed, since I might have some randomness that pushes me in different directions. R is the reward function. It specifies what reward I'll get for taking action A from state S when I end up in state S primed, and this can also be a probability distribution. Gamma is the discount factor. We won't need to worry about it for this set of videos, but it captures how valuable reward in the short term should be relative to reward in the long term. You need it for problems that potentially could go on forever. These 5 objects perfectly characterize an MDP. This is all you need to characterize your environment. It's important to note that in reinforcement learning problems, the agent doesn't have access to P or R. It has to learn about these as it interacts with the environment. Given we have this MDP, how does an agent go about making decisions? The agent uses what's called a policy. The agent observes it's in state S, and since it's in a Markov decision process, this is all the information it needs, and it uses this state S to decide what action to take. For example, if I'm in the bottom left of my grid world, then I could specify I always take the action up. But this can also be a probability distribution. For example, I could say up and right are both equally good, so let's do a 50-50, and I'll end up in one of them. The goal of the agent is to learn the optimal policy, which is the policy that, in expectation, gives me the highest cumulative reward. There are lots of ways to go about learning an optimal policy. For example, policy optimization, Q-learning, model-based reinforcement learning, etc. For these videos, we won't need to worry about this. Okay, so to make this formalism a little less intimidating, we can go through some examples and talk about how you would set them up as Markov decision processes. For our grid world, there are 9 states, depending on where the agent is, and we can number these 0 through 8 as pictured here, and so our state space has size 9. I also have my action space, which has 4 different actions, up, down, left, right, and I can number these as well. You might wonder what happens if I'm in the bottom left square and I take the left action. Is that going to be a problem? The answer is no. We can specify our reward function to punish the agent for doing illegal moves and just return it to the same square. Or we can just return to the same square until it takes a valid action. So we don't need to contract our action space in any way to fit the rules of the environment. We can specify the rules using the transition function and the reward function. As an example of what a component of the transition function in this case could be, we have a deterministic environment. So if I'm in state 3, right, the middle state, I take action 3, so move up, I should end up in state 7 with probability 1. This will be one component of the transition function, but it's going to specify every possible transition I could make when navigating the environment. For the reward function, there are a bunch of different reward functions that are going to specify the same optimal policy. One example here would be if I get 1 reward for ending up in the top right state and 0 reward if I don't. So this component here would be the only non-zero component of the reward function. So I get reward 1 if I end up in the goal state, regardless of where I came from, and any other transition I get 0 reward. Alternatively, I could give +1 reward every time it gets closer to the goal state and -1 reward every time it gets further away, and this would have the same optimal policy. The difference, though, is that this reward function would be easier to learn from because it gives what's called denser feedback. And so reward design can be an important part in training an agent to do some specified behavior. As a more complicated example, we can look at the Atari game Breakout. In this case, you have pixels as your observation instead of a location component. The observation here is the image, so how do we capture that with a set of numbers? We use the set of RGB pixels to capture the observation. So let's pretend this image here is 41 by 41 pixels. Then we can then we would get 3 different 41 by 41 matrices with numbers in 0 to 255, specifying the color intensities of each of the 3 colors. To make life easier, we can consider a grayscale image. This is fine since the color isn't important for this game. And so in that case, our observation becomes just one single 41 by 41 matrix. You might think this is fine, but the problem is that this choice of observation makes the environment fail to be fully observable. Right? I have no idea what direction a ball is going if I just get this as my image. Is it going left or right, up or down? I don't know. So this isn't a good choice for the observation. Instead, a better one would be to stack images or frames together. And so the agent can compare where the ball is in these 3 images and use that to figure out the trajectory of the ball. So this lets us observe the ball's trajectory and is a better choice for the observation. Given that, what should the action space be? Well, here it's nice and simple. The paddle can either move right, left, or stay in the middle. So there are 3 different choices for our action at each time step. The transition function here will be very complicated due to the size of the state space, but does exactly what you'd think. The ball keeps moving on its current trajectory, taking actions move the paddle in the ways that you would expect, and hitting walls and bricks changes the trajectory of the ball, with bricks vanishing when they're hit. An example of what the reward function could be is every time the state st plus 1 has 1 less brick than the state st, then I know I've destroyed a brick and I get 1 point, and it's 0 for any other type of transition. That would try and destroy as many bricks as possible. We could also punish it for losing lives, but the original reward function would work for trying to get us to destroy as many bricks as we can. As a final example of something that wouldn't be done on a computer, you have a toy helicopter moving around the real world. What would the state space be in this case? Well, it could be the location of the helicopter in 3-dimensional space, as well as the angles of the helicopter, since I want to know how it's tilted to the vertical and to the horizontal. We're also concerned with how these components are changing. So how is it moving? How is it rotating? The action would be specified by applying different forces in different directions. This could be done through the controller, though it is the reinforcement learning agent that is using the controller, probably via some program, rather than, say, a physical human doing this. This could be a continuous action space. That's fine. Reinforcement learning can handle continuous action state spaces. The transition function would be determined by Newtonian physics, how forces affect the different motions of the helicopter, as well as things like wind resistance or gravity. All of these things will come in through the transition function. The choice of reward function is going to depend on what we want our helicopter to do. One choice would be, if I don't want my helicopter to crash, I could just say +1 reward when you're above a certain height and 0 reward otherwise. So the helicopter will be incentivized to stay above the ground, and so it won't be able to crash. An alternative would be if I wanted to get to a certain location, I could use minus the distance from this location as a reward. So in trying to minimize this number, so as to maximize its reward total, it's going to want to fly to that location. So this would encourage it to fly to the place I want it to go. We could also have reward functions to incentivize complicated maneuvers, things like front rolls or 360 spins. These are going to be really complicated and hard to specify by hand. But there are methods like imitation learning or inverse reinforcement learning that would let you create a reward function that incentivizes that sort of behavior. So that's how reinforcement learning problems are set up. One of the key ideas that Vanessa is interested in is called regret bounds. So we're going to talk about that here for an illustrated example. Imagine a game with 1 state and 8 actions. The image you want to have in your mind here is that there is an agent picking between 8 different slot machines, and each slot machine has some different probability Pn of giving you $1 when you pull the lever, and the rest of the probability 1 minus Pn that it will give you nothing. The goal of the agent is to get as much reward or as many dollars as it possibly can. The best strategy would be to pull the machine that's the most generous, with the highest probability of giving you money, and just keep pulling that machine over and over. That would be the best thing to do. The problem is that the agent doesn't know what these probabilities are. It has no idea what the reward function is at the start of the game. So it's going to have to explore to get estimates of these payout probabilities. But exploring inevitably involves you having to make decisions that are suboptimal. You're going to have to pull machines that aren't the best one when exploring, and this leaves for some reward on the table. The concept of regret is the amount of reward that you have to leave on the table. So what you do is you compare yourself to some optimal person who knew exactly what to do from the start and just pulled the best machine every time. How much reward did they get in expectation? And compare that to how much reward your partial exploratory policy gets in expectation. That's how much you missed out on, and so it's your notion of regret. Okay, so how do you approach this problem and try to minimize your regret? An obvious thing to do would be to say, I'm going to try and estimate each of these probabilities that these machines have, and I'm going to estimate it as Pn is approximately the number of times it's paid out divided by the number of times I've pulled the machine. So if I pulled the machine 100 times and it's paid out 56 times, my best estimate is that the probability is 56%. I can do this for each machine, keeping track of these numbers. This makes sense, but which machine should I pull? This problem is still open. There are a couple of different ways you could go about trying to learn the optimal policy, with different regret bounds for each. One thing you could try to do is just pull machines at random at the beginning so you can learn something. Then at some point, just pick the machine you think is best from that point onwards. And that machine might change. You might pick a machine you think is best, not get paid out 20 times in a row, and you say, okay, that wasn't the best machine, so I'm going to move to my new estimate of the best. But your action is always determined by which machine you think is best in the present moment. This is called a greedy policy. Someone might say, well, the problem there is that if I get the wrong estimate of the best machine at the beginning, I might never pick it. So my regret is just going to keep building up. So maybe I should explore some proportion of the time consistently. So another policy I could have is 90% of the time I pick a greedy policy, right? The best thing I could do. So I don't leave too much regret on the table. But 10% of the time I'm going to pick a random action so I can learn more about every machine. So over time I should be able to figure out which machine is the best from my exploratory policy, but 90% of the time I'm going to take advantage of that. And this is called an epsilon greedy policy. The problem with this, though, is that 10% of the time I'm still accumulating regret. So another policy that I could have is to decrease the rate at which I explore over time. One way I could do this is to decrease the rate harmonically. So every time step, the probability that I take a random action is 1 over t. So on the 100th action, there's a 1% chance I take a random action, and a 99% chance I take a greedy action. And on the 1000th time step, there's a 0.1% chance that I take a random action, and a 99.9% chance that I take a greedy action. So I decrease it over time. That's another way to do it, and that's called a decaying epsilon greedy policy. So we can look at the regrets for each of these methods, and both greedy and epsilon greedy give you linear regret bounds. With time, the regret diverges, but it's always bounded by a linear function. Whereas for decaying epsilon greedy, the increase in regret is decreasing, it's tending to a smaller number, so this policy will be better than the other two. In this case, there's a very clear thing I can do to bound my regret, but in most complicated problems, it's not going to be this simple, and there won't be an obvious choice for how I should behave. Bounding regret in more complex problems is a very difficult thing to do. It's something that Vanessa is particularly interested in, because if you can bound regret, it can give you safety guarantees, and Jack will talk about that more when we talk about Vanessa's research agenda. So before we finish, we'll talk a bit about Bayesian reinforcement learning. The idea of Bayesian reinforcement learning is to use Bayesian reasoning to try and solve an MDP in an ideal way. The agent has a bunch of hypotheses and a prior distribution, and it's going to update this prior to a posterior. So what does it actually have hypotheses about? Well, in reinforcement learning, the hard part is that you don't know what the transition function or reward function are at the start of the game. They're unknown to you. So the agent has a bunch of hypotheses about what the MDP actually is, meaning what the transition and reward functions are. Each one of these hypotheses specifies an MDP, and you can have a bunch of these hypotheses and allocate different prior probabilities to each one based on how likely you think they are. As it gets new information, it can use Bayes' rule to update its prior distribution over the hypotheses towards MDPs that seem more likely based on the evidence. As it gains more information about which MDP it is in, it can use methods like dynamic programming to figure out how to behave optimally. As a simple example, we can imagine an MDP with just 2 different states and 2 different actions, which appears in the bottom left here. There are 8 different transitions, since there are 2 different starting states, 2 different actions, and 2 different final states. So 2 times 2 times 2, we get 8 different components to our transition function. We'll also assume the reward function is deterministic here, so each transition has some fixed reward number it gets. An example of a hypothesis in that case appears in the bottom right. Each transition has some probability of happening, right? Each action you take from each state, and each of these has a reward. This would be one hypothesis, and the agent would contain a bunch of these about, a bunch of different hypotheses about which environment it's actually in. As the agent takes actions in the environment, it's going to update the probability of each hypothesis towards the one that seems to fit the data best. So for example, suppose I'm in the state 1 at the beginning of the game. I take the blue action 10 times in a row, and every time I end up back in state 1. The probability of that happening in the bottom right MDP is 0.5 to the power of 10, which is really, really small. That doesn't seem very likely. So if there's a hypothesis that has p being higher than 0.5, that hypothesis will begin to look more likely based on this evidence. The specific way we would update is using Bayes' rule, but generally the concept is that the hypotheses which don't fit the data very well will get downweighted, and we're going to hopefully converge to the true hypothesis, the true MDP that we're actually in. This seems really ideal, The problem is that Bayesian reinforcement learning isn't really feasible for realistic problems. The hypotheses are just too complicated and too numerous. Given that, why are we interested in Bayesian reinforcement learning at all? Well, Bayesian reinforcement learning can serve as a benchmark to compare other reinforcement learning methods too, since it's sort of the ideal way to do it. Comparing deep reinforcement learning algorithms to Bayesian reinforcement learning can actually be quite difficult, since deep reinforcement learning doesn't really have any theoretical guarantees as of yet. But nonetheless, Bayesian reinforcement learning can serve as a good benchmark. In the next video, we'll talk about ICE agents, which use Bayesian reasoning to update a very specific choice of prior. So this will be relevant for that video. But the main reason Bayesian reinforcement learning is important to this video series is that Bayesian reinforcement learning has a bunch of issues to do with it, beyond just being infeasible. Even if it was feasible, these issues would still persist. Infra-Bayesianism is motivated to solve these problems. Jack is going to go into more detail when he talks about Vanessa's research agenda as to what these issues actually are and how Infra-Bayesianism aims to solve them. If you want to learn more about reinforcement learning specifically, there are a lot of great resources out there. I have found David Silver's reinforcement learning course a great introduction to the core concepts and to the different types of algorithms used to solve reinforcement learning environments. The spinning up and deep reinforcement learning resources on the OpenAI website are also very good, and they include Python implementations of lots of successful algorithms. So if you're interested in writing your own algorithms, that one's a bit better. If you prefer reading a textbook, Sutton and Barto's introduction is one of the best resources you can find on how to learn reinforcement learning. All right, I will see you in the next video.